All right, welcome. So what we're doing today is we're discussing the kinetic molecular theory, and in particular, we are going to derive some important temperature-based and kinetic energy-based formulas that come from the kinetic molecular theory. So let me explain. So this kinetic molecular theory is really a way for us to describe and understand the behavior. See, we know currently that from experimental evidence that we have our current relationships, PV equals nRT, and if we derive, we have PV over T equals PV over T, and all the other derivations that come from this. All right, we know from experimental evidence that, of course, those relations exist, but kinetic molecular theory is a way for us to try to understand, okay, get some understanding of how this all works. Try to explain the behavior. We know the behavior experimentally, but how do we explain it? And through the explanation of why it all works, why those certain relationships work, pressure, volume, temperature, moles, we come to an understanding that there is a unique unifying idea, and that is that there's kinetic energy, and that kinetic energy, which is the energy of motion, is tied to all of these types of relationships. And we learn that temperature and kinetic energy are directly related through this type of analysis. So we're going to derive some kinetic molecular theory type of equations that are based upon kinetic energy and temperature that come from our trying to understand how gases behave. So in any case, let's get started. And be crazy and go in order. Let's start with the assumptions. Now, these assumptions that I'm writing here, these assumptions help us understand how gases must behave in order for the current understanding of how these relationships are tied together. What I mean by that is we know PV equals nRT. That's the ideal gas law. And the reason why we say ideal is because under these assumptions I'm going to list, gases are behaving under these ideal ways so that this formula or all other gas law equations that we derive from it are true. So the first assumption is gases are random. And that makes sense. In order for gases to, let's say, expand outward from a balloon and move in ways to make a balloon bigger as, let's say, temperature goes up. So when the temperature goes up, volume goes up, okay? In order to understand all of that, okay, it must make sense that gases are moving in a random nature, okay? Two, which is kind of tied to this, gases, of course, okay, have no attractions for each other. If they did attract each other, then they wouldn't move independently in random motion, and they would be coalescing more like a liquid. And the calculated volume that we get if we increase the temperature would not be what we expect because they're acting more like a liquid and less time pushing outward. All right. Three is that these gases are very small. We say they're so small, these gases don't get in their way and bounce off each other and never get to produce the pressure to push out the volume if we increase the temperature. Now, of course, temperature and volume are proportionate. That's, of course, if the moles are constant and the pressure pushing on the outside are constant. But in this case, these particles are so small they don't really get in each other's way, so that they're hitting each other more than they can get to the container. So we say that their volume, the volume of the individual gases, are really insignificant. Very important. All right. And then we say that these gases, when and if they do collide, they don't really get in the way, but they will collide with each other occasionally. The energy from the collisions are elastic. And that means that the energy is definitely conserved, elastic. All right, collisions. So if you have two molecules, and let's say one is going slow and one's going really, really fast and one's going really slow, this one will hit it and it'll give its energy to this one, and now the speed at which you'll hit the container wall will be combined with the energy it just grabbed. So its energy is combined, and maybe this one, like a cue ball, this one that hits this and transfers its energy, okay, will now be motionless like a cue ball if you play pool, okay? So that's what we call elastic. Now, inelastic would mean that maybe one would hit another and then they would stay stuck to each other, okay? And that's would not be good, because then we wouldn't have what? Gases being random. They would be kind of attracting each other, and one, two would not be satisfied. Okay, getting rid of that. So the fifth one, for all this to work, and the crowning jewel probably of all of this, is that kinetic energy, the energy of motion, is proportionate, it's a proportion sign, to temperature. Now that temperature has to be absolute temperature. That means temperature, that's Kelvin temperature, the real zero position. Zero temperature, zero kinetic energy. Okay, so those are the important assumptions that we must have. Now we're also going to have some governing equations. Now we're going to derive, okay, the relationships of how gases work and what pressure looks like based on these assumptions using some governing equations, okay, and then of course we're after some new formulas that will appear from this derivation. So we're going to call governing equations. These are equations that already exist in physics that we're going to utilize to make some sense of these relationships. So the first one, okay, is kinetic energy. Kinetic energy is equal to 1/2 mass mu squared. And this mu is velocity, okay? And so that's basically, you can think of it speed with direction, but its unit is meter per second, which is distance per second. It's speed, but it's, in physics we call it a vector quantity because it has directions, but essentially it's the speed. This is mass, and 1/2 the mass times the speed squared is how much kinetic energy, and this would give us a unit of joules, an energy unit. All right, moving forward, we got number 2, okay, and this would be frequency of collisions. Frequency of collisions. We're going to build a pressure formula from all of this, the frequency of collisions. Think about collisions. Well, first for me, it depends upon basically how fast they go. So that's the velocity, that's my mu. So the particles have to go a certain speed. The higher the speed, guess what? The more frequent their collisions with the container walls. And then I do know it's probably inversely, definitely inversely related to its volume. If the space is bigger for the same number of gas particles, they're going to collide less often. So higher space, volume is the space they fly in, lower the frequency, an inverse relationship. And then we're going to take that and times it by n. I can put n here, and let's kind of go over some semantics here. Okay, n, all right, is a value that tells me the actual. So n is the actual number of particles. All right, and if you remember, to do that, we take Avogadro's number, Na. We're going to call that Avogadro's number, Av number. That's what Na is, we'll just say, because I want to use that in our derivation. And if I times that by mole, we use little n, lowercase n for mole, right? If you think about this, I have 1.5 moles, and 1 mole is equal to what? 6.02 times 10 to the 23. So if I have 1.5 moles and I want the total number of particles, I would take 1.5 moles and times it by that number. Okay, so just important that you understand this is the total number of particles. How fast they go in the space they're in will give me the frequency of collisions. All right, now number 3, when we consider particles and their energy and how frequent their collisions, we have to think about the impact of their collision, their momentum. And we'll use impulse to describe their momentum. But when you think of momentum, you think of the impact. Pressure is force over an area. So what kind of impact or force, we're giving here? And it's mass times velocity, and velocity we're using mu. And that's essentially what we're using here. So we would say, we would make this proportionate here. Okay, it's a proportionate sign, and I should have made this a proportionate sign. Okay, to have an equal sign, I would have to have some constant that we've learned. So these are proportionate signs. Okay, and so this is the same thing as momentum. And so we're ready to rock and roll here, so let's get started. All right, so let's get started, and so let's try to define pressure. So pressure is inversely related okay, to, well, the collision frequency, or the frequency of collision. So I'll just write it here, frequency of collisions times the impulse or the momentum, the impact of the collisions, right? You think about how often they collide, and what kind of, gosh darn it, what kind of, impulse or momentum and impact, okay, do they collide with? Remember, heavier, because mass times velocity, the heavier an object is, the more it's going to have harder to stop, and the more it's going to slam against the container wall. And of course, the faster it goes, same idea. So it's just times the I. Okay, so I'm multiplying these two together, and that should give me pressure. Pressure is force over an area, and so how many collisions you have times their impact should give me that. So let's put the numbers in. So pressure, well, let's put the equivalents in now. So frequency of collisions is going to be mu, the velocity, times the actual number over volume. All right, and we're going to times that by the impulse, which is the momentum, it's mass, times the velocity, which is mu. The first thing I can see is that both of these equations, okay, have mu in them, more velocity, okay? I hope you understand. Okay, I know, it's terrible. All right, now, what I'm going to do is going to put them together, all right? So pressure is proportionate to N over V, all right, times, I'm going to keep this separate for a reason we'll see soon, m mu squared. So I just multiplied and just kind of simplified. Not kind of, I definitely simplified. Although this may not look like I'm simplifying at all in this uh, lecture, but hey, I'm trying to. Okay, so we have this relationship of pressure. Okay, using our basic understanding of how this all works. And I want to talk about what this value is here for a second. Okay, this mu squared, okay, is an important value when you think about this. Mu is velocity. This is velocity, and what we call this is the square mean velocity. Now, what the heck does that mean? Well, remember, as we should understand, look at the speed of gas molecules and look at the number. Let's put n here. N is the number of molecules. We know that there's going to be a big range of speed for a gas. There's going to be some going really fast, really slow, and a lot of them are going to be around the middle part of the bell curve here. There's a whole range of speeds for gases. Some hit each other and go fast. Some might be that cue ball that sits there quietly after it exchanges its energy elastically. Okay, so there's a range of speeds. So this is basically the average. So when we talk about the velocity, okay, of gases, we're really talking about the average. So this is the square mean velocity, just something to be aware of. Okay, any case, so now we're going to move toward getting rid of this proportionate sign. And this is kind of a strange thing because pressure is proportionate to all this, but we want to go equal. And I want to be able to use this because proportionalities are great. Hey, this goes up, that goes up, but I want to actually know if this goes up this much, exactly how much does the other one go? And we need to get rid of that. So what we understand is that there are three dimensions that the molecules can travel in. Okay, there's the Z right at you going into the board, up and down, the Y and the X. And when we think about it, pressure is equal to force over an area. Okay, and area, if you think about it, is two dimensions. But if you think about surface area, okay, like a force plate, let's say if you look at a syringe, and if this syringe here, and if I push down the syringe and make the space smaller, we're going to feel a lot of pressure pushing upward. But don't we have some pressure pushing outward? We do. But we're only going to measure the force pushing in this direction against the surface area here. And there's also, coming at you and away, right? There's three dimensions. So to quantify this, because pressure and molecules or the force over an area is due to what? The collisions, and the collisions are going to be random, if that's how this all works, they're going to be in all three directions. All three what? All three dimensions. But we're really only measuring the pressure in one. So to really get a value, we're going to take is the tire pressure, and we're going to take a third of it because we're going to be measuring with our equipment just the surface area of just one dimension. We're pushing up here. okay? We're going in this case, the y. We're using the y dimension, okay, to measure the pressure, but we're not considering the x or the z directions. So we're going to take a third of the pressure. And now that I'm just taking a third, now we can do some quantitative values. So by me going pressure is a third of, we're taking a third of the collisions just to measure, because it's random, it's going to be a third, right? I'm just going to measure what? The collisions that are going to hit my one dimension here, and that's what makes this come out from a proportionality to a equivalent, okay, equal. So 1/3, and because we have the rest, let's get rid of some stuff here because it's going to cramp my style. All right, so we have pressure equals 1/3, and get the rest of this, N over V times M mu squared. Okay, now so next thing I'm going to do, sounds like a strange thing, but I noticed something. I have M mu squared here, and if you look at one of the governing equations, mu squared is here. All we need is a half in front. We got kinetic energy, and I want to solve for the molar kinetic energy. That'll make more sense in a second. So I want the kinetic energy to come out. So what I'm going to do is I'm going to multiply this side of the equation by 1/2. And then I'm going to multiply this side of the same equation by 2. And if you notice, 2 times 1/2 is 1. So basically I'm taking part of this and timesing it by a half, and part of the same side timesing it by 2, and essentially 2 times 1/2 gives me 1, so I can do that. Sounds strange, but I'm timesing by 2 and then dividing by 2, and this will have no effect. But in the meantime, what I get here is pressure is equal to 2/3 N over V times, and this is what I wanted to do, 1/2 mu squared. And so party person, what I have here is I have my kinetic energy. And that's important. I want it to come out. So rewriting this, pressure is equal to 2/3 N over V times the kinetic energy. All right, cool beans, but I'm still not where I want to be yet. Okay. Now, if I remember that this N, which is the number of total particles that gave me the frequency of collisions, is equal to Avogadro's number, we're going to use Na for that, times, okay, mole. That's the equivalent. All right, so that's the equivalent of N. And I'm going to put this equivalent of N in place of N right here. Now, let's do that. So P, pressure, is equal to 2/3. All right, I'm going to put the equivalent in, and because we used the black, we're going to be Na times N over V times the kinetic energy. Okay, what the heck did I do that for? Well, party people, okay, I can do that because they're equal to each other, but more importantly, if I take the kinetic energy and I times it by Avogadro's number, which is the actual number of particles, this is the kinetic energy per mole when I multiply this together. So I'm going to take this part of the N, which is the Na, Avogadro's number, I'm going to times it by kinetic energy. What I'm going to get is kinetic energy per mole. And we're going to put a little squiggly here to say that, hey, that's per mole. What else do I have left? Well, I got P equals 2/3 N over V times Ke squiggly. All right? And Ke squiggly is equal to the molar kinetic energy, which is the kinetic energy per mole of gas particles. Okay, well, we're trying to solve for that. It's one of my first equations. Now, what we're going to do here now is we're going to kind of do some simplification here, and I am going to bring over the volume and the moles. I'm going to bring the mole and the volume over to the left-hand side, and when I do that algebraically, okay, I'm going to get PV over N equals 2/3, and of course that's times kinetic energy, wait for it, squiggly. Okay, now what do we know? Okay, well, we know that kinetic energy, let's go back to one of our assumptions, kinetic energy is proportionate to temperature. You know that. All right. So I know that this is proportionate to temperature, and PV over N might be proportionate to temperature. Oh, wait a minute. PV over N. Let's think about this. PV over N. Temperature. Wait a minute. Is this proportionate to temperature? Now, I'm going to put proportionate because I don't have an R. If I had an R, it'd be equal. If you don't see what I'm talking about, solve for P. If I solve for P, isn't it P is proportionate to what? NT over V, right? PV equals what? PV, I'll leave the V here, equals nRT. If you remember that, that's the universal gas constant. So since PV over N, okay, if you solve for, and I'll just show you, PV equals nRT. And if you think about it, bring the N down here. Okay, now it's equal because the R is there, but if the R isn't there, you have what you call a proportionation. And so that's what it is. So what I mean by all of this is that on both sides of this equation, I'm just going to clean this up, the equation I have left standing, okay, both sides of this equation are proportionate to temperature. So both of these are proportionate to temperature. When this is proportionate to temperature, you eventually get PV is proportionate to NT. And of course, when you find R, it becomes PV equals nRT, which is, hey, the ideal gas law. And pretty interesting, just using our explanations of how gas laws work, we wind up getting the formula that we get from experimental work. So we know we're on the right track here. So that's a kind of cool aside, but I'm going to take this apart now. All right, I'm going to take this apart, and let's just go up to the top here. And so 2/3 times kinetic energy squiggly, write that right up here. 2/3 times kinetic energy squiggly is proportionate to temperature. Okay, now to get this equal sign, okay, to get this equal sign, we add the universal gas constant into here. So 2/3 KE squiggly molar kinetic energy is equal to RT. Okay, let's solve for kinetic energy. Kinetic energy, molar kinetic energy, is equal to, well, now wait a minute. I'm going to get rid of that, right? So I'm going to solve for that. So this is going to be the inverse. If you do your algebra, it's going to be 3 over 2 RT. And that, my friends, is the first equation. Kinetic energy squiggly, which is molar kinetic energy. It's the kinetic energy per mole of a gas. And what's really interesting about this, and you can pretend if it's not, all right, is that the kinetic energy, the motion energy of a gas, okay, is not equal to temperature, as you may have heard in other courses. Hey, kinetic energy is the average. No, it's not. Kinetic energy is actually 1.5 times a gas law constant times temperature. All right, so it's not the average kinetic energy, although we use that in other courses. Kinetic energy is proportionate to temperature, but from our relationships, look at this. If I know my temperature, I know my kinetic energy. That's really important. So if I have two different gases, no matter what their gases are, if they're under the same temperature, now of course this temperature is absolute, it's Kelvin temperature. So if they are at the same temperature, they must have the same motion energy. That's really, really important. And if I know the temperature, just the temperature of a gas, I don't care how much, I know its molar kinetic energy. That's crazy. Just knowing the temperature of, let's say, methane, CH4. I know how much molar kinetic energy per mole just by the temperature by using this formula. I don't need to know its mass. I don't need to know how many atoms. Just knowing the temperature, I get the kinetic energy per mole. And that's a really important equation. One you don't have to memorize, but interesting where it comes from. Now, there's another one we have to get. So hold on to your seats and let's go get it. Okay, now we're going to pick this up, all right, where we kind of left off over here. Okay, before we times by 2 and divide by 2, I'm going to start back up here with this P. So pressure is equal to 1/3 It made it equal because we're picking a third of the dimensions, right, where the particles randomly hit, over V, okay, times m mu squared. So we're just rewriting this. This was, of course, a derivation as we went forward this way. Okay, and we times by 2 and divide by 2 to get the kinetic energy eventually. Not doing that here. Okay, now that we're going to go and get another important relationship. Now we're going to solve for the velocity, okay? And that's important part of this as well. So now I have this equation. Don't forget, party people, that n, which is moles, times Avogadro's number is equal to the total number of particles, all right? So what I'm going to do here is, again, I'm going to substitute this value in this position. And I did this once before, but I didn't take out the kinetic energy, so let's do that. So pressure is equal to 1/3, and that's going to be N times Na over V times mu squared. All right, cool beans if beans are chilled. Now, let's continue. We're going to do this for 1 mole, okay? And I'll explain as we go through, but N is equal to 1. So we're going to do this for 1 mole. So when you stop and think, if I'm doing this for, if N is equal to 1, and we're going to do this for a 1 mole equivalent, okay, we can see that this goes to 1. So if it's 1, it's just kind of going to go away. So I'm going to have pressure, let's go black now, pressure is equal to 1/3. Now this is going to go to 1, so I forget about it. It's going to sit there as 1, so I don't need this symbol anymore. Na, Avogadro's number, over volume times mu squared. All right. Now, we understand that we're now going to see something here that's pretty darn interesting, I think. And that is that if I take this Na and times it by the mass, think with me, Avogadro's number times the mass, boy, it's going to give me some number of grams. And because we're doing it per 1 mole, we're thinking about what? The mass if I have a mole of that gas. Okay, therefore, this right here is molecular mass, fancy M. So let's plug that in. At the same time, I'm going to algebraically move the V over here. Okay, so I'm just going to solve for the V next to the, I'm just going to move the V to the other side of the equation, multiply both sides by V over, well, V over 1. But bottom line, you should be able to figure it out that this becomes PV equals 1/3. Remember, this is going to be molecular mass, and this is going to be still mu squared. Okay, mu still there? Gotcha. All right, so I have this nice little relationship, and so not finished yet, we're getting close. Okay, and what I know is that PV is equal to nRT. Well, here you go. So because PV equals nRT, I could put nRT here in place of PV, and that equals, okay, 1/3 molecular mass mu squared. However, party people, n is equal to 1 in my system, so this goes to 1, so it's RT equals 1/3 molecular mass mu squared. Now we're ready to solve, okay, for mu. All right, so we're going to solve for mu. We're going to bring everything over to the other side. So what we get is we get RT. All right, now this is going to be 3RT, right? And the molecular mass comes here. I'm just doing simplification algebra here, guys. Okay, and that equals mu squared. We're almost there. Now let's solve for speed. Well, or velocity. We've got to square root both sides. And so what you get, party people, is you get mu, which we call the root mean square speed, right? And it's equal to the square root of 3RT, universal gas constant temperature in Kelvin, over the molecular mass. All right, and that is a very, very important equation. This tells me essentially the most common speed that molecules have. What I mean by that is, if you look at the distribution of speed, right? So here comes speed or velocity. I know speed doesn't have direction, but we're just going to say how fast meters per second. And this is n, number of particles. We know that at a particular temperature, a gas, all right, has a range of speeds. This root mean square speed is somewhere like right here. This is the root mean square. So this is where most of the molecules have the speed. It's right about the average. Okay, it's not quite the average because it's a square here, and that makes it a little bit bigger, but that's what we have to use in our equations. Why? Because we're dealt with the governing equations, especially the one right here with the square root. So we're kind of stuck with the root mean square that way, but it still works very nicely. So this gives me the most probable speed or velocity of the gas. Remember, gases can have a range. So there's going to be more what? If you count with me and think about this as a bar graph, there's a lot of gas molecules that are at this speed. That's why this part of the curve is high. Each X is a gas molecule. At this end of the bell curve here, there's less of them. Okay, so there's less gas molecules. This is the most probable speed. Okay, now this is really important to understand. If I give you another Boltzmann distribution graph, this is really important. Okay, watch this. If I have two gases at the same temperature, okay, let's make this argon. Okay, and let's make the red one helium. Okay, now we still have speed here, and this is the n, number of particles. They're both at the same temperature, so temperature is the same for each. Yet you notice helium goes what? Moves and has a lot more gas molecules that have greater speed than argon. What gives? We just found out that if you're at the same temperature, right, at the same temperature, you must have the same kinetic energy. So we have two gases that are under the same what? Temperature. They should have the same kinetic energy. And what did I learn? This is important. Kinetic energy is equal to 1/2 mass velocity squared, correct? So both of these have the same energy, kinetic energy. But careful, if they both have the same kinetic energy and someone has a greater mass to keep the same number, it's got to have a what? Lower speed. Yeah, the heavier gas, argon's molecular mass is about 40 grams per mole. Helium is about 4 grams per mole. So argon is going to have a lower speed for the same kinetic energy because it has what? Higher mass. It takes a lot more energy to move a bigger particle than a little bit of particle. So even though these both have the same temperature and same kinetic energy, okay, argon's going to have less velocity because it's going to use up part of its kinetic energy to move bigger particles. So it's going to move slower, and therefore its root mean squared speed is going to be what? Lower than that of helium. Or helium is going to go faster and have more molecules going faster than argon. Why? Because look at this relationship. I'm almost done. Stay with me. As the molecular mass decreases for helium, the root mean squared increases. So the lighter the gas, the faster the most probable speed occurs, the faster this gas moves, even though they're at the same temperature. Very important. Okay, so we're going to use this formula, okay, which is the root mean squared speed, and this is molecular mass. Be very careful though. These formulas are going to be in joules. Okay, and joules are kilogram per meter per second squared. Okay, and so therefore because you're in energy, you have to be in kilograms. So this molecular mass will be in kilograms here. Temperature, of course, in Kelvin. So careful with your units. Okay, a joule is actually a kilogram meter per second squared. So therefore, our molar mass will be in kilograms per mole. That's the only little catch there. And of course, this doesn't have any mass. All right, so I hope that helped. All right, so a lot of work here that gets us to two very important equations, the molar kinetic energy that shows that kinetic energy is equal to temperature, okay, times R. okay, times 1.5. And of course, the root mean squared, the most probable speed of a gas, is inversely related to its molecular mass. So we would say that the root mean squared has what? It has the inverse of the square root of its molecular mass. Bottom line is, it's an inverse relationship. Okay, good luck.